I can make a lot of understanding on what is going through your mind, even if you are not aligned with the class or the flow of the presentation. So that, in that sense, it's a serious limitation, virtually presenting. But then since I know for a fact that most of you are aligned to electrical and also to teaching as a profession, I do expect that you will go along with me along the stream. And then in the end, if we have time, I would ideally be looking forward to your questions, doubts, or anything that is there in the minds. Energy efficiency improvement through electric motor is like a foundation, basically. Motors are the prime movers, and they offer you the foundation for building a sound, reliable, and energy efficient system. When we say system, we include all the end-use energy, consuming equipment like fans, pumps, blowers, HVAC instruments, your compressors, crushing, or any other instrument that you use for shape change in the raw material, and the material handling, importantly. So these are the three areas where motors are chief implements. And as we progress, I will try and position you with respect to the importance of motor as a system component, and also about the push-pull effects affected by the standards and efforts taken by industry experts, like including EMA, Motor Management Association, and then standards by the Bureau of Indian Standard and the international standards. The topic today is avenue for energy conservation in thermal power plants. Only a couple of slides are there that will address the applications in thermal power plants, but by and large, applications of motors are prevalent across the cross-section of the industry use. Therefore, any one of you keenly interested in only addressing the thermal power plant applications, we could have some question answers answered, so that my experience in dimensioning motors or supplying motors, or even examining motors at site for their reliability and performance can be discussed. So let me go into the topic. This slide is here in order to create a funneling effect. I am trying to put you in the picture. So far as our Indian electrical economy is concerned, as you all know, in 1947, when we got our independence, the total generation in India was 1362 megawatt. It has grown to last year, March, the official figure is 3,82,150 megawatt. This is the virtually all new installed capacities in the post-independence era. So from being an agriculture economy, we became an industrialized nation. And today we talk about Make in India, Skill India, and so on. Just to give you a picture to understand this 1362 in the right perspective, Chennai's own requirement of power in May, June, July, which are the hot months in Chennai, the requirement is around 2,500 megawatt. Chennai city alone, Chennai metro, and that of NCR, National Capital Region, which includes Delhi and some surrounding cities like Gurgaon, Faridabad, Ghaziabad, and so on. It is around 11,000 megawatt during summer months, when the AC will be fully utilized. So that gives you an idea as to how meager was this 1362 when we got our independence. From there, we have built this capacity. And what is our road ahead? When the economy becomes urbanized economy, where by 2030, it is expected that approximately 80% of our population either will live in the big cities or eke out of big cities, like supplying to the requirements of big cities like milk or vegetables or fruits and so on. So 2030, CE has projected that our country's requirement will be 8,17,254 megawatt, approximately double from the present position by 2030. This is if the economy is keeping pace with the urbanization and other demands that are created routinely. So we have an unenviable situation where we are a growing nation. We are the youngest nation in the world and the most aspiring nation in that sense. So that gives a lot of challenges in meeting these kind of projected demands, and what is actually happening on the resource side. Our population tripled in 20th century alone. Whatever that we consumed from the earth resources till the 19th century, we consumed equal amount of earth resources in 100 years, that is the 20th century alone. And it is not relenting. It is continuing to consume that kind of earth's resources. Look at coal. Coal estimated reserve is 130 years. And coal, as you all know, thermal power stations, the topic of today, contributes even today 62% of the total power generation in India. This has to be reversed. India will be the only country which will continue to depend on thermal power stations by 2050, while most of the countries, including China, would have had a negative growth in thermal power generations. So this is one dangerous thing that is awaiting us. Oil, as you all mostly know, the reserve available globally is only just 50 years. Oil also handles the transportation and some power generations in standby generators and things like that. However, what is abundantly available is the non-conventional energy like biomass, solar, wind, nuclear, etc. You must be knowing that the government came with a solar program.
Slide is not visible.
Slide is not visible. Why is it not visible? Okay. Is it visible now?
Yes, sir.
I think Shyam, when you started the introduction, this happened. Anyway, should I go back? Should I go back to this slide just to give you? I assume this slide was also not visible. This was the first slide after the introduction. Is this slide visible?
Visible, sir.
Visible, and can we move forward?
Yes, sir, please.
Yeah. So this was a slide on which I was commenting about the available earth resources, both in terms of fossil fuel, coal, oil, and the abundantly available non-conventional energy, renewable energy. While on this slide, I was making this commentary about what India has achieved in terms of the solar power capacity. For mitigating the green gas emission, India had assumed a very tough target of 35% of GHG emission limits over the 2005 figure. 35% is not small. The only country which has a larger than India's share is China, which is 65%, and China is not achieving its target. Whereas India has achieved the target in the year 2021 itself. What was supposed to be achieved in 2023, India has achieved 2 years ahead of time. So India is well positioned to go ahead and create history in terms of the renewable energy as a quotient towards the total energy development. When we talk about thermal energy, we all know that we are over dependent on thermal energy even today. One of the most problematic area is the amount of water that a thermal energy consumes in creating the power generation in India. So water is another source which is depleting very fast. If you look at the water footprint, people claim that there are only 2% of the total global water population, although 3 times the global, the earth is surrounded by water. The potable water quantum is just 2% available. So that is also fast depleting, and we will soon have a difficulty in finding water potable for drinking. So human consumption will have to be probably treated and consumed, and that is a dangerous situation in one another earth resource that is available for us. So this is what India agreed in the Paris Agreement after the Kyoto Protocol on the green gas emission. 33 to 35% below the 2005 level by the year 2030. So China has got 60 to 65. USA, after signing the agreement, went back during the Trump administration. They agreed for reduction of 26 to 28%, but they did not agree to continue to do it. Europe has also, by and large, achieved this kind of targets, and there is very little that Europe can do for future developments. So, as you know, the energy efficiency offers you the largest opportunity for energy saving, followed by the renewables. So in terms of the push effect, government has brought the policies for solar and wind projects. As you can see, when they originally announced, solar was 100 megawatt, 1 lakh megawatt, and 60,000 megawatt was the wind. Wind capacity was at that time around 20,000 megawatt. So additional capacity of 40,000 megawatt was to be built with the wind opportunity, wind assets. Why is this happening? Shyam, why is this happening?
So actually, there is some issues.
I don't know. I don't know if it happens. Allow me to please come back and then flash my slides. Yeah. So solar 100,000 megawatt. We have achieved that already. So there will be newer policies. So in terms of renewables, the push effect has been created by the government of India. Potential is 32%. Whereas the energy efficiency has the largest opportunity available for the industries and other consumers. We will talk about industry today because we are talking about generation through thermal power stations. So we'll move on. So we chose rightly the foundation for the energy conservation activities within any large energy consuming industries, including power generation. So motors, as we all know, are the workhorses of the industries. And we'll go on to establish the importance of motors in the scheme of things for primary energy efficiency achievement. As we all know, in any industrial application, if you take thermal power station, then we'll be talking about auxiliary power as the energy consumption, self-consumptions of the thermal power stations while producing electricity. So even there, the contributions for energy consumption through electric motors is almost 70%. And I have another graph on the left-hand side where motors contribute 74% of the total energy consumed in normal industries. So we'll have to talk between the industry applications and the specific applications in the thermal power stations for auxiliary power consumption for our understanding of the topic. As you know, heating, electrolysis, and lights or IT loads contribute approximately 12 plus 11, 23 plus 8, 31. Approximately 31% of the balance requirements in the industries are met through these processes: heating, induction heating, electrolysis process, and IT and lighting loads. So therefore, motor becomes the single largest implement through which the highest energy efficiency is accounted. If you look at the energy consumption in a power generation, typical breakup of auxiliary power consumption, there are three classical examples taken here: 500 megawatt generating station, 210 megawatt generating station, and 110 megawatt generating stations. So if you go down and take a look at this auxiliary power consumption, approximately 7% is the benchmark when it is a 500 megawatt power station. 8% is the benchmark when it is 210 megawatt power stations. And 12% is the benchmark when it is 110 megawatt. What are the loads? ID fans, PF fans, FD fans. There are also other loads: ash handling, coal handling, conveyors, and so on. So typically, electrical motors out of 8% will be almost contributing 70% of the total energy consumption, even in the case of auxiliary power consumption. If you compare, once again, a typical industry application vis-a-vis the auxiliary power consumption in a thermal power plant, you will notice that ID, FD, and SA fans are contributing 40% of the total power. Boiler feed water pump will be 25%. And your condensator waste pump and fans will be 27%. Others will be 8%. These others would be BOPs like ash handling, coal handling, conveyors, crushers, and so on. So this is how the total auxiliary power consumption is shared. Similarly, in the case of an industry, you will find that variable torque loads are almost contributing 66% of the total power. So we talk in terms of air compressors, fans, and pumps, almost 2/3. Other motors will be the process motors, like shape-changing motors in the case of raw material to finished goods. Similarly, material handling, conveyors, and so on. So this is how the motor's own consumption is laid out. We will come back later on to discuss and understand more about this variable torque loads or centrifugal loads, which are used as pumps, fans, and compressors or cooling compressors, refrigeration compressors. So, is somebody trying to say something? If nobody is talking, I'll move on. So the agenda for energy efficiency prospects through motors or motor system will be like this. So for motors, influence will be on site and supply conditions, sizing of the motors, and standards to be followed for the motors. And in the case of a driven system, mechanical transmissions, cumulative system efficiencies will be discussed with respect to fan or pumps or any other driven equipment. And very importantly, we will include also a few slides on the effect of speed change through VFD or belt pulley arrangements or eddy current drive arrangements, in order to try and position how much of energy efficiency opportunities are available from these three focus points. So typically within the motor, self losses, when we reduce, the energy saving opportunity available is a single digit saving. Whereas in the case of the driven system and speed change, 2-digit energy saving is possible. So therefore, without belittling or dismissing motors as not so important, we have to build a case for including motor as although single digit saving is possible with motors by replacing motors, we have to include the quantum of reliability and energy efficiency that is available through motors, its own self losses reduction. And then we go on to build a case for driven system and speed change. I know for a fact that there are many speakers talking here on fans, pumps, VFDs, and so on. I will only be creating a platform, like I said, while depending on the motor as a scheme of things, the other two systems, driven systems and speed change, should also be addressed, and therefore I am bringing a few slides as we progress. When we talk about motor, there is a global harmonized standard available now. Most of you might be knowing. In case it is new for you, let me put you in the picture. The whole world of motors was divided between IEC and NEMA. IEC, as most of you know, is 50 Hertz country. NEMA, which is North American and some South American countries, were 60 Hertz countries. And therefore, there was a classical divide between the two worlds. While IEC was, forgive me, while IEC was using loss subtraction method for measurement of efficiency of motors, NEMA was using a direct efficiency estimation or efficiency calculation by measuring both the input as well as the output power. Output of a motor, as you all know, is the torque. So you need a torque to measure accurately the output power and then convert that into kilowatt, so that you are able to compare the output divided by input and arrive at the efficiency. Whereas in the case of IEC, we were taking the input power, subtracting the losses, and arriving at the output power as input minus losses. So therefore, efficiency used to be still output by input. But importantly, while IEC testing was being adopted by most of the world, we were assuming stray losses as 0.5% across board for all the outputs. That was disputed in the year 2002, and by the year 2007, a new efficiency testing standard was adopted as IEC 60034-2-1. That was the first time that IEC adopted a new efficiency testing standard, where they talked about accurate measurement of stray losses. And 2-1 in 2014 was a revision where only one method was permitted for efficiency measurement under the IEC. Now that gave rise to IEC 60034-30 in 2008, where globally a harmonious standard was required, and therefore IEC and NEMA agreed upon new efficiency standard, international efficiency standard as IE1, IE2, IE3, IE4 and so on. Today we are discussing IE5, not yet adopted, but a few manufacturers like pump manufacturers have come with IE5. But with the induction motors, the growth in efficiency is from IE1 to IE2 to IE3 to IE4 presently. One or two slides I will try and cover the higher efficiencies, the limitations of induction motor technology and so on. So in India, we adopted this IEC 60034-30 as IS 12615 2011. The original standard in IEC came in 2008. We were behind by 3 years, and in 2011 we adopted IE standards in India. In 2018, including an IE4 efficiency and dropping IE1, India has now efficiency standards for IE2, IE3, IE4. So any one of you interested in further implementations or choice of recommending or advising any of your industry clients, or you would like to undertake some class studies on IE technologies adopted by the IEC, we can give you more inputs on that. So in India, what really happened was again a push effect, where the government of India through a GO, Gazette order, came with a order where they said IE1 motor will be banned effective 1st October 2017. Actually, this got implemented effective 1st January 2018 after 3 months of grace period. So effective 1st January 2018 in India, IE1 motors cannot be manufactured, cannot be sold even by the dealers. So people who are resellers of motors cannot sell IE1 motors or non-IE motors per se. So minimum is the IE2. In India, minimum efficiency performance standard, MEPS, is IE2, whereas in Europe, effective 2014, IE3 has become MEPS, minimum efficiency performance standard. So Europe is ahead of us, so is the US. So the Western market, so to say, have adopted higher efficiencies, and they have also increased the global presence of IE4. So I will just briefly touch upon the 3 technologies available for motor manufacturing. What is familiar to us with over 130 years of existence is the induction motors. Fairly new are the 2 other technologies, which is permanent magnet, PM motors, and switched reluctance motors. These 2 motors are synchronous motors, while the induction motor is asynchronous motor. So therefore, while we talk about replacing the induction motor for higher efficiency potential through permanent magnet motor or switched reluctance motors, in other words, PM SM and SR SM. So this is how motors are referred to in the market. So these 2 can comfortably meet IE4 or even IE5 whenever it is adopted, while induction motor will have limitations in going beyond IE4 efficiencies. Now, if you take a look at the technology per se, as we originally discussed, the most matured in terms of technology on a scale of 1 to 3 is the induction motor, followed by permanent magnet motors, and then the switched reluctance motors. And in terms of high peak efficiency, induction motors offer you the lowest among the 3 to meet the challenging efficiency levels, including part load efficiencies, while permanent magnet or switched reluctance could be leaders in order to offer you higher efficiencies. So the future of IE4 motors or IE5 motors, greater than IE4 motors, will be permanent magnet or switched reluctance motors. but almost 99% of the total motor populations will be asynchronous motors induction as of today. So let's take a look at the market or the manufacturing quantum for the the motors. I have taken a scenario as published by EMA, Indian Electrical Electronic Manufacturer Association, for the year 2015-16. The total motor population, that is manufactured motors and sold in the market, as reported by all the EMA members, motor manufacturers, was 57.49 lakh units. Now, 57.49 also includes the fractional horsepower motors used mostly in appliances. So approximately 43.05 lakhs, or 75% of the total motor population, are FHP motors sold in the appliance market. While the integral horsepower sold in the agriculture and the Indian industrial market is approximately 14.44 lakhs. That further gets divided into AC motors and DC motors. As you can notice, DC motors are fast depleting in terms of manufacturing standards and in terms of manufacturing practices. Only 4,000 units out of 14.44 lakh units. So nearly 99.9% of the motors sold for the industries and agriculture are AC motors. And the AC motors are further classified into four: HT motors, which is 3.3, 6.6 and 11 kV motors; flame-proof motors with specific applications in safe areas; low tension slip ring motors, again going out of fashion, going out of manufacturing, because AC motors with VFD are capable of replacing the slip ring motors for the purpose of high starting torque. Similarly, DC motors for the purpose of multiple speed variations available across board. That means we now have approximately 93% of the total motor population sold in the industries as LT squirrel cage motors. So our focus, our attention will be more on this when it comes to further manufacturing, because it's not changed. I have data for about approximately 15 years of manufacturing as reported by the motor manufacturers under EMA. This figure is more or less identical. It has not changed. So as we move on, we will see how this is important for us, for our understanding. So low tension squirrel cage motors, induction motors are the important focus for our understanding today on energy efficiency. I also have another EMA slide, not necessarily made by EMA, but made with the statistics shared by EMA. As you can see, in 2017, 87% of the total motor manufactured, which you saw previous slide, approximately 14.4 lakhs, out of that 87% were non-IE motors. Before the GO from the Government of India, Ministry of Commerce and Industries, Department of Industrial Policy and Promotions, DIPP brought it, 87% of the motors were non-IE motors. Only 10% were IE, 10 plus 2, 12% were IE2 or IE3. IE4, of course, at that time was not available extensively in India. In 2018, even after the GO from 1/1/2018, EMA reported, perhaps it must be up to March end, 70% of the population is non-IE motors. IE motors grew to around 30%. And in the year 2019, almost 95% of the motors manufactured are IE2, IE3 or IE4. Minuscule percentage of IE4 is also there. But still we have 5%, which is probably spillage. I am expecting that to 2020 or 21, this would have completely disappeared. And all the motors manufactured and sold in the market today in India through EMA members must be IE2 or IE3 or IE4. IE2 is compulsory, IE3 is voluntary, or IE4 is also voluntary. Now, while this was taking effect, the Bureau of Indian Standard also came up with this change in the standard for, basic standard for induction motors in India from IS 325, which got abolished, to IS/IEC called dual standard, IS/IEC 60034-1. So once this was adopted, there were about 425 motor manufacturers in India before the abolition of IS 325 with approved IS marking and all that. But once the IS/IEC 60034-1 was adopted, only 99 licensees renewed their BIS license. So today we have what would you call as aggregation. A lot of non-serious players have dropped out, and only serious players are existing today with the new standard after the IEC 60334-1 was adopted. Also importantly, the Government of India came with the suggestions that all motor manufacturers should punch ISA mark of the BIS. So this also helped us to limit the number of motors that will get imported in India. India was an importing ground. So that was limited primarily because most of the manufacturers outside the country, except one or two in China, did not come up to get their motor plant tested by Bureau of Indian Standards and approved by Bureau of Indian Standards for marking their motors with ISI. Since you are an academy people, I can readily share the name. LG compressors, LG equipment in Coimbatore were the only ones, in my opinion, who took the Bureau of Indian Standards to China, to one of the plants from where they were buying almost 10,000 motors every year imported, and get that plant certified by BIS and buying motors from China with ISA marking. Otherwise, most of the market is now with the Indian motor manufacturers. These are basically some, foundations or informations that would help you to understand the motor business per se. Standards and things like that are coming in the few slides down the line. So it's also important for us to take a look at three classifications when it comes to typical industrial applications with motors. I divide them into three. Process machines, applications involving process machines where for example, crusher, grinder, mixer, agitator, extruder, where shape change takes place of the raw material. Whereas in the case of utility machines or auxiliary machines, like fans, pumps, blowers, compressors, vacuum pumps, and roots blowers, you saw approximately 66% of the total motor applications are in this area of utility machines, where the machines aid manufacturing, don't necessarily get involved directly in the shape change. So auxiliary machines are mostly centrifugal in nature. Important for us to understand this as we progress. 66% of the total power consumptions are through utility machines or auxiliary machines, which are largely centrifugal in nature. And the third and last application area for industrial motors is the material handling or transport machines, where we use cranes, hoist, conveyor, bucket elevators, escalator, lift, winches, and so on. So these are applications where motors are used, and between material handling and process, approximately 33% would be the total energy consumption fed through the motors. So 66% is accounted by utility machines, and therefore our thorough understanding on the opportunities available for energy saving through utility machines, either through optimization or through higher efficiency or through adapting speed variations in order to optimally meet the process flow, will be important. So what is efficiency? I'm sorry if I'm sounding a little elementary, but then many of us need an understanding on this. So efficiency is a percentage expressed as output divided by input. So, or in other words, output plus losses. Or still it will be input minus losses divided by input will be the efficiency. We can measure the input power to the motor through a power analyzer. Quite easy to deal with inputs on both denominator and numerator. Therefore, what would make the difference is the losses. So in order to achieve energy efficiency in a motor, higher efficiency in a motor, the losses must be reduced. This has to be understood. There is no tinkering with the output of the motor. Output is a standard. For example, if you have 11 kilowatt or a 15 kilowatt or a 22 kilowatt motor, and that is never disturbed, that is never discussed. What is happening is the reduction in the input through the reduction in losses. Therefore, energy efficiency in a motor is achieving reduction in losses so as to improve the overall energy efficiency of the motor. Now, what are the typical losses? Most of you in the education field, academic field, will know these are the typical losses in a motor. You have core losses, which is iron losses, which contributes to approximately 20 to 25% of the total losses. Stator ice core or stator copper losses is approximately 34%. Rotor losses or rotor copper losses, which is slip losses or air gap losses, is around 21%. Friction and windage losses, which is sometimes clubbed with the core plus windage and friction. We call it as IFW, iron friction windage losses. Can you please put that mic off? Iron friction windage losses are sometimes called as no load losses. So no load tests will reveal the total iron friction windage losses. If you look at the stray losses, I have put this under the red box. Primarily, the objective is to discuss what has happened with the new IE rule to the stray load loss measurements. So let's look at some of the standards. I don't know if you have already noticed. Normally, I use 3 I's for my presentations. Information, interaction, and then instructions. Now, I'm not going to handle instructions for today's class because you are not the kind of people to whom, if it is industry people who are interested in replacing existing motors or undertaking better maintenance of motors, then I would have resorted to instructions. But today's audience requires more of information and interactions. So I expect that this presentation would be making only information available to you. These slides, I'm sure, will be made available to you by the organizers. If you have more input required, you want to elaborate, we want to get more input available from us, we will be able to share, or it is also available from the internet freely. So we'll go ahead and see a few important standards that are used in the industry for applications. Like I mentioned, the dual standard IS/IEC 60034-1 2004. This became the general standard for rotating electrical machines from the year 2016 or 17, if I'm not mistaken. Then you have IS 12615 2018, which is the latest edition, which includes IE2, IE3, and IE4, 2-pole, 4-pole, 6-pole, 8-pole, from 0.12 kilowatt to 1000 kilowatt in all the 4 poles. So efficiency values are declared. Some of the performance values are also covered by this standard. India standard is the only standard where performance standards like starting current, pull-out torque, starting torque, etc. are mentioned in the standard. This is for protecting the interest of the consumer. Then let's take a look at the scope of this IS 12615. Briefly, I will quickly read so that it makes better sense to you. This standard covers single speed motors. So dual speed motors are not coming under this standard. 3-phase, single phase don't come. 50 hertz, in India 60 hertz don't come. Cage induction motors, any other motors are not covered here. Of motor voltage will be rated for 1000 volts or less. We typically have 2 ratings, 415 and 690 under the LT. Have rated outputs from 0.12 kilowatt up to 1000 kilowatt, 2-pole, 4-pole, 6-pole, and 8 poles. There is a unique standard IS 1231 which says the frame size to output has to be met up to 315 frame size in order to ensure that motor manufacturers don't flout this rule, so that you are, as an industry user, able to buy any make of motor meeting the boundary dimensions stipulated under IS 1231 or IS 2223 or 2254, which are for flange mounted and face mounted motors. These motors are rated on the basis of either duty S1, which is continuous duty, or S3, intermittent periodic duty, with rated cyclic duration factor of 80% or higher, which in other words simply says it is S1. So other than S1 duty motors, the standard is not applicable. For S2 or S5, S4 or S5 or other, the standard is not applicable. These are again for designed for operations in virtually sinusoidal and balanced voltage conditions. Although the nameplates of motors will carry plus or minus 10% for voltage, plus or minus 5% for frequency, and plus or minus 10% for absolute value of these two put together, the standard clearly stipulates that the efficiency is available only when the motor operates with balanced loads and without fluctuations. Again, motors should be designed for an ambient temperature of 40 degrees centigrade and an altitude not exceeding 1000 meters. When the altitude exceeds 1000 meters, derating has to be applied. And when the ambient increases beyond 50, because motor manufacturers now adopt up to 50 degrees centigrade, beyond 50 again, the standard is not applicable. And then these motors are generally provided in IP55. So again, the scope document includes motors IP54 or higher or superior. And the method of cooling for these motors is according to IC 411, which is self-cooled fan at the non-drive end of the motor for cooling. And the service factor not exceeding 1.0. I don't know. There is nobody talking today or tomorrow about compressor. If there is somebody talking about compressor industry is one where service factor 1.1 or 1.15 is freely used, but that is not recognized by the Indian standard or even IEC standard. So this is the scope document. Very briefly, I have covered IS 12615 2018. If you are interested, can be downloaded or can be purchased, and then more details will be available from the original document. IS 15999-2-1 is equivalent of IEC 60034-2-1, which was originally written in 2007. I mentioned it to you earlier. When a standard common, was required throughout the world, IEC revised their standard as IEC 60034-2-1 in 2007. India, along with IS 12615 in 2011, also adopted the testing method similar to IEC and named it as IS 15999-2-1 in 2011. This standard, I have used a slide from Siemens Limited, who have put up to now, in my opinion, the only lab where they can test these motors with the residual loss method, which is the only method recognized by IEC 60334-2-1 in 2014. So this lab can test motors up to 3 megawatt. Only lab in India which is accredited by NABL, and the testing is done. And this lab costed Siemens approximately 70 crore investment, just for information on the sites. Then we move on with the standards. IS 13555 is the guide for selection and application of three-phase induction motors. I do not know, since you are from the academy field, you may not be directly interested, but if you are academic, then you are akin to reading. I expect that you will do a lot of reading and grasping of the topic per se. So therefore, I am putting up this number in front of you. IS 13555 is the guide for selection and application of motors. It has got a wealth of information. Also will help you to appreciate the fact that the industry per se at large do not pay a lot of respect or heed to what is recommended in this standard. If they do, then they will not freely replace motors from one location to another location, one application to another application. Misapplication in industry is possibly the largest reason why the motors fail. Approximately 60% of the failures, in my opinion, are because freely people replace motors from one application to another application. In that sense, IS 13555 requires a lot of understanding, thorough reading, and use in applications. Then I have put two standards parallelly. These are guides for selection of cage induction motors when used with VFD, IS 15880 and IS 15881. Again, these two standards give a wealth of information as to what should not be done when you are adopting a VFD for speed changes in your motors for a 2-digit energy saving, which is available from the system. So therefore, these two standards are again very, very interesting standards. One has to read, understand, and apply. They are mined and also during procurement of motors. So let's look at new purchase of motors. Then we'll look at replacement of motors and the speed change. So those are the future topics. New motor purchase, when we make, we have to consider the duration factors in motors. Duration factors will be because of voltage variation inside. Typically up to 10, 5, 10, as you can see here, 10% voltage variation, 5% frequency variation, plus or minus 10% combined voltage and frequency. Supposing you take 7% variation in voltage and frequency, 3% is the variation permitted in order to achieve this 10% combined. So up to this level, the motor need not be derated. But once this deviation goes beyond 10%, the motor needs deviation. That means when you select a motor, you have to select a motor with this deviation applied. Similarly, plus or minus 15 and 5, total 15% variation, the motor output will be derated by 90%. Similarly, for ambient temperatures, up to 50-degree ambient, no deration is required. But once it goes to 55, 5 degree more, or any part of 50 to 55, 5% is the duration. Now you might ask, as per mathematical progression, we should also publish 60 degree, 65 degree, and so on. No, motor manufacturers caution that the motors are suitable for a combined, temperature, including temperature rise, to about 65 plus 5, 70 plus 50, 20, 120. So this is what they are recommending. With the hotspot allowance, another 10 degree, 130 is permitted for class B rise. So beyond this, not only the temperature rise of the motor, but also the performance of grease and bearings have to be considered. Therefore, the motor manufacturers clearly indicate that any temperature, ambient temperature beyond 55, motor manufacturers should get involved in designing a motor with adequate cover and protection and give it to you. Therefore, any duration for temperature or temperature rise should be limited up to 55 degree ambient. Similarly, altitude, up to 1000 no duration required. Beyond 1000, for every 500 or part thereof, duration is applied. For example, Ooty, which is 3000 meters above mean sea level, the duration applicable is 14%, or 86% of the motor rated power will be available at high altitudes. For those who might have entertained questions in their mind as to why in high altitudes the motor has to be derated, let me answer up front. The quantum of oxygen or the air available density will be very, very low as you go up from the mean sea level. And therefore, since the air is the coolant medium for cooling the motor, there will be limitation in the cooling of the motor and therefore the derating. Then the voltage variation, I have a commentary here. Although the variation permitted is plus or minus 10% or 15%, you can see here in this graph, 0 is the rated voltage, which is 415 in India, 0. So anything on the negative side or on the positive side, the performance will vary. As you can see, full load ampere will be high as the variation increases, and then also as the variation decreases and variation increases, also the ampere will increase. So similarly, power factor will change from one end to another end. But efficiency is the only factor which is affected on either sides. The efficiency of the motor goes for a toss because of the voltage variation. So typically where you apply a new high efficiency motor like IE3 or I4, you must ensure that the voltage variation is not like 10% or so. So this is a factor which need to be understood by the industry people. They can't claim that I purchased IE3 or IE4, but I am not getting the energy saving. Voltage fluctuation or voltage variation is a very undesirable component when it comes to implementing energy efficiency. We also will talk about the voltage unbalance. Voltage unbalance is not similar to voltage variation. Voltage unbalance is the unbalance in 3 phases. So as you can see here, for up to 1% unbalance, it is permitted. The variation in current will be 6 to 10%. It is permitted by the standard. But anything more than 1%, there will be duration in the motor output. or the efficiency will reduce as the unbalance increases. So as you can appreciate, the unbalance in voltage is also undesirable. Just one slide on oversizing, which happens generally thanks to consultants or contractors. I don't know if you will ever come to this situation in your academic career, but if it does, I can expand with more slides on selection and things like that. I have presented on selection of motors for variable torque load, constant torque load, and metal handling applications. So those slides can be made available for some of you who are interested in understanding what variations need to be adopted. But here in this one slide, I am trying to cover that a consultant specification calling for star delta starting for an ID fan application with a very high inertia of the impeller demanded that the 110 kilowatt motor is selected in a larger frame size. The moment you go to a larger frame size, efficiency will come down. Can you please put off the mic for the consideration of the other people? Kindly, it is disturbing. Please.
Yes, sir. Yes, sir. Meeting, sir.
Why don't you mute everybody's mic? Anyway, there will be a question and answer session so that this disturbance does not take place. My request to you. Thank you.
Sure, sir.
So as you can take a look here, a 55 kilowatt motor, because of the high inertia and star delta starting, which is called restricted starting, requires a selection of a 110 kilowatt motor. The moment you choose a motor which is almost double the size of the BKW of the fan, the efficiency goes for a toss. So we need to restrict selection of motors. The ideal choice here would be to select a star delta, select a DOL starting or a VFD starting, so that 55 kilowatt at best can be 75 kilowatt, not 110 kilowatt. So this is just one slide, a commentary on how inefficiency creeps in when you select a motor based on the consultant specification. Only commentaries, I am not dealing in details. So the retrofit opportunities are the next opportunities available for replacing the existing motors and adopting higher efficiencies. Here is a slide which we use for the NMRP program, National Motor Replacement Program. If you look at the total population of motors, we have about 2.5 crore motors installed in our country. 25.1 million is 2.5 crores. This is the total population of motors considering all frame sizes. And if you can look here, 63 to 132, generally called as small motors, that is between 0.18 kilowatt to 7.5 kilowatt, they constitute approximately 83% of the total population available in the market. 83%. This 160 to 200 frame size, which is 11, 15, 22, 18.5 is there in between, and 30 kilowatt, up to 30 kilowatt, they constitute approximately 14% of the population. So between small and medium sized motors, approximately 97% of the motors of the total population are contained, while larger motors, which are 37 kilowatt to 180 kilowatt or even beyond, that is 225 kilowatt to 355 frame size, contribute only 3% of the total population. And the estimated percentage that could be replaced as given by NMRP is 50% of these motors which are below IE1 or non-IE motors. Around 30% of this population can be replaced with IE3 or IE4. Similarly, 10% of this population can be replaced. Difficult to replace this population because these are costly motors. So payback estimates could be very low. So based on that, approximately 1 crore 15 lakh motors are available for upgrade to IE3 in our country. So NMRP has been started, again a push effect or a pull effect, let us say, to create awareness among the industries and invite industries to come forward and replace in large scale existing non-IE motors to IE2 or IE3. NMRP is specifically for IE3. So approximately 1 crore and 15 lakh motors are available, but I would imagine that NMRP has not been a big success in spite of being there in the last 4 years, because they have achieved a very, very small number of approximately 10,000 motors replaced with some large industries. We are in discussion with some leading industries in Tamil Nadu also, but the success rate of NMRP is not very high, because in our country, we either need a stick or a carrot. The stick came in the form of MEPS, IE2, if you recollect that slide. The carrot has not come because there is no incentive for buying IE3 motors and replacing existing motors. If there were to be an incentive, let's say in terms of income tax rebate and so on, our industry would have been motivated to make investments. But I'm just making a commentary based on the information available through this slide. So Energy Efficiency Services Limited has come up with the NMRP, and this NMRP, as academicians, if anybody is from industry approaching you, large industries, you can please tell them to undertake large-scale replacement of old inefficient motors with new motors, being the foundation of, you are building the other assets over it, like replacing pump, fan, or compressor. Without replacing the existing motors with a higher efficiency, that would not yield the kind of expectations that you have. The slide should have been avoided, but I'll still go ahead and make this. This is that instruction part I talked about initially. I am the one who will not use instruction in this class. You are academicians and you are learned people. But then when it comes to, I'm also seeing some speakers are talking about energy auditing and energy auditing tools. So I will just briefly explain to you as to what we do as an approach to a replacement of energy efficiency with the existing motors. So what we do is, first step, we prepare inventory. The inventory is a comprehensive list of all plant motors, then dividing them into small, medium, large. And then, based on the year of manufacture, the number of times it is rewound, and the criticality of application and so on. The inventory is again segregated as small, medium, and large. Then we carry out an initial load survey. For this, our people need not go. Auditors need not come from outside. Industry plant engineers can carry it out themselves. While doing this exercise, we also recommend them to prepare another Excel where they will work out the load factor, number of hours of operation, and type 2 coordination, which typically talks about the protection control circuit available for the motors. In each motor starter box, what is the contactor, relay, or any other protection cable, they can be listed, and then they can be compared with the standard ISIEC standard is available in order to either improve or replace the existing control protection circuits. Then the third, based on these two previous inventory and initial load survey, is to prepare a key motor identification. Now we have a chart available based on which, on a scale of 1 to 10, anything which scores more than 7 would be the key motor in an application. So that would include the number of rewound, repair, number of hours of operation, load factor, and so on. So a key motor, once it is identified, then those key motors can be the candidates for replacement upfront, whereas you would further want to explore and see how this can give you the return on investment, and therefore we recommend load mapping. For load mapping alone, on a reduced key motors list, you can invite external auditors like us. We can come and put load mapping or complete profile mapping and give you a final list which you can use for undertaking large-scale implementation of IE3 motors. I have a slide here where we talk about increment between IE1 to IE3. A case is a 2.2 kilowatt 4-pole whose original efficiency was 79.7, which becomes 86.7 in the case of IE3. So using this chart, which is like I already told you, around 97% of the total motor population is below 30 kilowatt as per the EMA statistics, we can undertake a desktop audit with which an Excel sheet calculation will be able to give the management the encouragement to invest and replace motors up to 30 kilowatt without doing any of the load mapping or profile mapping. So that is the choice available to industries. This slide is here primarily because my objective was to tell you that the original IS 4889, which was replaced as IS 15999-2-1 in 2011, 4889 is for testing efficiency of the motor as per loss subtraction method. A Bureau of Energy Efficiency code project is available from the internet, where you could see how a motor efficiency can be estimated at site by measuring no load and load test. As you can see here quickly, load test is done, no load test is done, and then the loss calculations are made, and then we arrive at the load factor and the efficiency, operating point efficiency of the motor. In this case, it is 11 kilowatt 4-pole motor. In this case, it's a 37 kilowatt 2-pole motor. It is possible to make on-site efficiency estimation and also project the payback estimate. Here it is 11.9 months. Here it is almost 45 months. So one could be persuaded to also undertake on-site efficiency estimation and then shortlist the motors which could be replaced on a large scale basis. Anybody interested in this topic will have to necessarily get in touch directly so that we can discuss this further. Now let us go into system approach. Now, motor system comprises of, as you all know, motors, including variable speed drives, controllers, transmission elements, and the end-use applications like pump, fans, compressors, refrigeration, and so on. In all these three, best practices is included as a common factor. So you have best practices in selection, maintenance, repair, replacement of motors. You have best practices in motor systems in selection, application, replacement of old inefficient systems, and also in the case of pumps or fans, compressors, as a replacement opportunities available. Therefore, scope available through best practices and system component changes are going to provide the industry an opportunity to improve overall effectiveness and the overall efficiency of the system. This slide will tell you what are all the factors that affect the motors internally and externally. Power quality will have an impact on the motor performance, as you all know. And the equipment used for transmission distribution of the power, like transformer, switchgear, and cables will have an impact. Cables in terms of voltage drop and so on. Then the controls like contactors, soft starters, variable speed drives have an impact on the motor performance. Motor per se by itself has inefficiencies built in its system by age-old practices. Coupling, mechanical transmission elements have an impact on the performance of the motor as well as the efficiency of the system. Driven equipments and their efficiencies and their internal losses also have an impact. And the mechanical controls and process like throttles, valves, dampers, and pipes also have contributions to overall energy efficiency of the system. So when one undertakes the complete energy efficiency, they should factor and consider all the kind of losses in the total system. We call it as cumulative efficiency. One case in front of you, which probably Mr. Patterson will deal in extension maybe tomorrow, are the various losses in the system and how to improve by design or by replacement. So as you can see here, motor, belt, bearing, and then the impeller. All the losses are going up as heat losses. So we all know that when you convert energy from one form to another form, in this case from electrical to mechanical, the losses will be available in yet another energy form. Here it is heat. So energy cannot be created nor can it be destroyed is proved in this class. So therefore, when we look at the total system, the output in terms of flow and pressure will give rise to the cumulative system efficiency, output divided by the input. So as you can see here, with all the losses factored, we arrive at a system efficiency of 56.4%. It is possible to get a single digit saving from these three elements, that is motors, belts, and the bearings. And a 2 digits energy saving opportunity is available through impeller replacement or the total system replacement, such that the efficiency can go up to as high as 75%. So 2 digit saving in the system is possible if you address the total system as a whole, not just the motor. Again, we saw this slide in a previous form. I have explained this, so I leave this slide for later on for your view to basically impress on you the fact that motors are surrounded by all these system components, and some way or other they impact the performance of the motor. Performance in terms of reliability or in terms of energy efficiency are impacted by all these surrounding systems over the motors. So therefore, motor has to be taken good care of if it has to live long. Almost 99% of the failure of the motors are inflicted on the motor from external sources. This has to be understood. So one slide on how the power transmission element can offer you energy saving. As you can see here, for a continuously loaded fan application or a belt-driven pump application, replacing existing V-belt with a flat belt or compact V-belts nowadays, you will be able to achieve up to 5% energy saving minimum. So when one undertakes a replacement of motor, one can also consider including the transmission element so that the total energy saving potential is augmented. 3 to 5% becomes 5 to 9%. This is the choice available. Somebody is handling a class on energy auditing equipment or tools. So I'm just flashing this figure. These are some of the tools which we use in our routine audits. So we go to the last choice that is available for improving energy efficiency, which is through speed variations. We saw in earlier slide that almost 2/3 of the population of loads in the industries are variable torque loads or auxiliary power loads or utility loads, fan pumps, compressors and fans. If you look at the opportunity available for energy conservation, 60% of the potential for energy saving will come from system optimization. Usually fans and pumps are oversized in industries for a situation which will never arise in the industry life. So people typically oversize, and therefore they struggle to optimize the actual throughput with respect to the input. If you optimize through mechanical system optimization, you have approximately 60% energy saving potential. The electronic speed control, or in other words, VFD, will offer you 30% energy saving. So 10% is the energy saving available through motors. Let us put actual numbers. Supposing you were to imagine 20% total saving. Out of that, 60% will come from optimization, pipes or pumps or ducts or whatever. So 60% of 20% is 12%. 30% of 20% is 6%. 12 plus 6 is 18. That means with the motor, just 2% is the increase in efficiency that is possible. This is why I was prompted to say in one of my slides that motors per se offer only single-digit energy saving, while the system offers you a substantial higher percentage, 2-digit energy saving possible. Keeping this in mind, let's look at motors plus VFD together. And there are a few slides which will explain to you what is normally done and what is normally done wrongly by the industries today. Before that, let me just give you one slide where I'm trying to compare the optimization using a throttle control in the case of a pump. So when you throttle, 10 by 10 is the normal dimension, original engineering design of the pump. This is 10 on the flow, which is Q. P is the head, which is in meters. So if you put 10 by 10 as the original design curve for the pump, you are in this curve. And this is the design optimum load where 100% power output is available from the motor and pump put together. If you throttle in order to optimize your flow from 10 to 5 or 10 to 7, let's say, what will happen? The pressure will increase. Throttling will lead to pressure increase. The curve has shifted, performance curve has shifted now, yet there is a power saving available, and that is up to about 11%. When you reduce the flow rate, even though the pressure increases, the product of Q into P will give rise to a reduction in power from 100 to 89, which is 11% saving. But if you were to do that with VFD, where there is no throttling, mechanical throttling is not involved, no friction involved, you come to 7 and you also come down from 10 to 6.4. These two are optimum points and you remain in the same performance curve. And this will give rise to approximately 55% energy saving. So this is the gain of using a VFD instead of an output valve. So these are the important factors for us to consider for advantage of using a VFD with the motor. This slide will explain to you the 4 different torque characteristic of the load. This is not that of the motor. Motor's whole time job is to deliver what the load demands. But we have to understand what does the load, what are the characteristics of the load. This one first is torque inversely proportional to speed, where the power will remain constant, HP. This is an American slide, therefore HP. You can read it as kilowatt. The torque will reduce as the speed increases. This is the x-axis for speed. Some of the applications are winder, rotary cutting machines, or internal grinding machines, lathes and things like that. So as you increase the speed, as the component becomes grooved, well grooved, the HP or the kilowatt will remain constant, but the torque will reduce. So the motor should be capable of delivering the reduced torque. Similarly, torque is constant. These are applications like all our metal handling and the process machines, where the torque will remain constant throughout the change in speed. The power will increase in direct proportion to the change in speed. So these are applications which are largely used in industries like we already discussed. Torque is proportional to speed is another area where power becomes proportional to square of the speed. Calendars, eddy current drives are all examples of this. Torque proportional to square of the speed, which is the pumps, fans, and centrifugal compressors, gives rise to torque proportional to square of the speed and power therefore proportional to cube of the speed. So when it comes to using a VFD for speed variations to optimize the torque requirement or the load torque required by the machine, substantial energy saving or cube times energy saving is available by using a VFD. And therefore, for any pump, fan, centrifuges application, VFD is an excellent choice for energy conservation, the 2-digit energy saving which we discussed. So this has to be understood, followed by torque is equal to constant. Here, energy saving may not be much, but there will be smooth starting and smooth stopping. So for some of the machines like conveyors or even some applications where precise stopping and starting of machine in shape changes, VFD would be a good choice. So best choice is T is equal to proportional to N square, followed by T is constant. So this has to be understood as a principle for applying VFDs with the motors. Now, this is a slide from IEC 60034-17. Part 17 deals with the inherent losses within the motor. What you see on the left-hand side here, I don't know if my cursor is visible to you. If it is, you will notice that there are 4 losses: iron friction, copper losses, rotor copper losses, and the stray losses. Whereas when you apply the motor with VFD, you will find that additional losses are there within the motor. So with the VFD, motor's own self-efficiency, self-losses will increase, and therefore the efficiency will come down. These additional losses are called as losses in the iron or additional joule losses. So independently, looking at the motor alone, the efficiency may come down. I don't know if you are aware, when the original IEC 60034-30 was announced, they had given IE2 motors with VFD will exhibit characteristic efficiency of IE1. IE3 motors with VFD will exhibit IE2 efficiencies. This was originally discussed. Today, of course, IEC has come with a separate standard for testing both motor and VFD put together. 34-2-2, if I'm not mistaken, or 2-3 is the standard now for testing VFD plus motor. So no more classification of IE3 when used with VFD will become IE2, or IE2 when used with VFD will become IE1. That is not any longer valid. And I think some of the leading manufacturers in India have also adopted it. So, but fact remains that when driven through a VFD, due to PWM wave, there will be additional losses in the motors. Motor's own efficiency will come down slightly, but then the overall efficiency saving, which we saw in the last two slides, 2-digit savings are available through efficiency improvement in the system, cumulative system by optimization. I have one slide just as a commentary again, where when a motor is used for VFD application, the motor should qualify as VFD duty motor. It should not be simply used with VFD, and the stress in the insulation or winding wire should not lead to failure of the motor because of the VFD. Therefore, the minimum requirement that a motor has to have to meet VFD duty is using dual coat winding wire, class F insulation, class F varnish, and also class SF insulating papers. Dual coat means polyamide winding wire instead of polyester winding wire available in the market. So dual coat winding wires followed by an impregnation in vacuum pressure. Instead of dip and cure, it should be vacuum pressure impregnation, or inverter grade treatment should be used to make the motor fundamentally eligible to be called as a VFD duty motor. Now, the second step is to understand that even after you do this exercise of making the motor qualified for VFD application, the temperature rise of the motor will remain class F to class F. IS 15881, which I introduced to you a few slides back, deals about this topic. The temperature rise will remain class F, utilized to class F. Now, utilizing temperature lower to class F to class B level will increase the insulation life of the motor. And therefore, whether it is a constant torque application or variable torque application with VFD, either torque derating has to be applied or higher frame has to be selected to restrict the temperature rise to class B. You will have some doubts. If you have, we will discuss this on the sides. For the present, I want to only proceed with what is offered to the market and what is tutored to the market in order to meet these standards. Consultants say, I want class F insulation, but the temperature rise should be limited to class B. How it can be achieved is what I have discussed in this one slide, but more details can follow on the sites in case you wish to engage me in discussions on this. So high efficiency motors, some people will have doubts whether I have to necessarily buy a IE3 with VFD, why I should not buy an IE2. Anyway, there is an additional loss in the motor. This one slide here, as illustrated by 60034-25, clearly states that higher the efficiency, the motor efficiency is retained with the VFD also, and therefore it's always prudent to use higher efficiency motors, I3 or I4. I have just given you one case example here, where in order to improve the energy efficiency, a sugar factory adopted for their boiler feed water pump from HT to LT conversion so that they can use a VFD. Now, high voltage VFDs are very expensive, whereas low voltage VFDs are cheaper. So they decided to convert the HT motor to an LT motor so that they can easily adopt a VFD for energy saving, after having observed and understood that they were using output valve for throttling the flow. So the motor existing was a 280 kilowatt 6.6 kV medium voltage motor. We otherwise call it as HT motor in 315 M frame size. So what we did was we replaced it with the same 280 kilowatt LT 415 volt, same frame size 315. Efficiency was marginal 96.4, from 96 to 96.4, but then this efficiency is accurately measured, unlike this efficiency which is based on assumed stray losses of 0.5%, as you can imagine. So we gave a calculation, we convinced the management, 3 boiler feed pump motors were replaced one shot using this method. And this is a slide I borrowed from the senior manager engineering from that group, sugar mill, which he had used for his MTech course for the units consumed and energy saving achieved by them by converting the HT motor to LT motor. Bottom line is they achieved a payback of less than 2 crushing seasons. As you know, in sugar, the crushing season is about 9 months to 10 months and not more, sometimes 9 months. So 2 crushing seasons, this payback was achieved. The investment was entirely paid back. This is almost 6-7 years from now. The industry is reaping the benefits of converting from HT to LT and then using it with the VFD. So that was my last slide, just as a case study and encouragement. I use that. I have now completed my presentation. Time is now almost 10:30, 10:26. So in case you have any questions, we will take it. For that, I will be going back and forth to the slides in order to elaborate on the answers. But in case there is no questions, you can have additional half an hour break. Thank you.
Excuse me, sir.
Yes, please.
Yes, sir. Sir, this is Jiva from Mechanical Engineering Department, sir, from Kumaraguru College of Technology. Sir, I just want to have certain clarifications on if you are converting these HT motors to DOL with HT motors to VFD with LT motors in. So what is the impact on the harmonics level, sir? Like when we wanted to estimate the harmonics, how is that? So it will be lesser or higher, sir?
So mechanical engineer is worrying about the harmonic. No, I am not finding fault with it. Yeah, you are right, sir. When we use a VFD, there will be generation of harmonic because VFD will give rise to non-linear loads. There will be harmonics, but the treatment of harmonic itself is external to the motor. You saw this slide where we talked about qualifying a motor as being suitable for VFD. Dual coat winding wires and the VPI impregnation will take good care of the standing voltage waves caused because of harmonics. So motor is protected from harmonic, downstream harmonic. The upstream circulating harmonics can be taken care by using various tools like detuned filters and active harmonic filters or passive harmonic filters. There will be harmonic. Your observation is very right.
Sir, with respect to the electric vehicle batteries, like the drives in, right? We use the DC motors in. Like how the standards are improving, sir. Whether we have any insights, we would like to know about any improvements in that DC motor on the aspects of DC motors with respect to the electric vehicles.
Sorry, I don't have any information on electrical vehicle motor used in electrical vehicles. You will have to find somebody, some other expert to give you more inputs. I don't have any information.
Sir,
I'm a left ear specialist.
Sir, one small input, sir. The electric vehicles will be having only DC motors, sir.
DC are servo motors. I am only very, I am not familiar with any of the technologies used or any of the selection procedures. Like I told you, 93% of the total population of the motors is induction motors. So I am worried more about the large opportunities available than drilling down my knowledge or experience or efforts into up and coming market. I'm too old for it. You'll have to find another expert.
Hello, sir. Good morning, sir.
Good morning.
Sir, I want to sir, feedback form on the WhatsApp group.
Sir,
Shyam.
any questions which is addressed to the speaker alone, sir, let it be discussed now, sir.
Third day feedback form, sir.
Shyam will take it. Shyam will take care of that.
I no meet the.
Yeah.
Participants, if you have any doubts, related to efficiency improvement in electric motors, you can discuss now. Feedback form already shared in the WhatsApp group, as well as I am mailing the feedback form. Soon you will get the feedback form. Any doubts related to electric motors, you can discuss with our expert.
Good.
Hello, sir. I am no guest. How do you?
I'm
Shyam,
sorry. I'm unable to understand the question.
Shyam, conclude, please.
Yes, sir. Sure, sir. Sir, really such a wonderful session, sir. And thank you so much for spending your valuable time with us, sir. And I'm very sure that your session is very informative and very useful to all the participants, those who have attended this session. And once again, thank you very much, sir.
Thank you,
sir.
Thank you. My
Yes,
pleasure. Thank you.
Yes, sir. Participants who have some additional queries, you can address it to him via email also. The email is available on the screen link. Thank you all. We will join for the next session, sir.
Thank you.
Yes, sir.
Thank you, sir.
Thank you and bye-bye.
Thanks, sir. Thank you.